Hey guys, welcome back to statistics. This week we're going to be talking about something called a hypothesis test. So to kind of give you an intro to that or introduce that topic, kind of think about what we've been doing. We have been estimating the values of things using confidence intervals, right? So when we talk about, like if I said, what do I think the mean height of the population is, or what do I think the proportion of likely voters is, or something like that. We're estimating the value of an unknown population parameter, right? And we did that by collecting a random sample and gathering data. Okay, so whenever you see a problem that says estimate something, right, that's how you know you're going to be using a confidence interval. Hypothesis test is a little bit different. It is designed to test something, to test a claim. All right. So whenever you see a problem that says test a claim, we're going to be using this new concept called a hypothesis test. And this tests a claim about an unknown population parameter using information from a sample that we collect. All right. So we see a lot of claims out there, and we want to be able to test those claims. So you might have a vitamin company out there that says if you take our vitamin, then you will grow 4 inches taller than you are now, right? So they make some kind of claim about their product, or you might get a like a car company that says our cars last the longest, or our will go well beyond the warranty of 10 years, or something like that, right? They're making a claim, and we want to be able to test that claim using a statistical analysis. Okay, so we're gonna introduce that and talk about that here, probably with the simplest of experiments. We'll start with something very simple, and then take a look at a few other types of experiments or claims that we can test. All right, so we're going to start with the experiment of flipping a coin. All right, so I have this coin. We're assuming that the coin is fair and has not been altered in any way. Okay, so then I go and I flip the coin 100 times, and I see 80 heads come up. All right, now I'm getting a little bit leery about this coin. I'm not, if I'm seeing 80 heads in 100 flips, I'm starting to question whether or not this coin is actually fair. All right. I'm not sure if it's fair or not. I mean, you could get 80 heads, but it doesn't seem like it's very probable. All right. We expect to see about 50 heads, right? If the coin is fair, we would see 50 heads and 50 tails, or something close to that number. We're not going to get exactly 50. Maybe we can get 55. Maybe we would get 60, maybe even 70, but 80, I'm not sure about. All right. So there is always the possibility that we could get 80, but what is that actual probability? That's what we use to kind of determine whether or not this coin is going to be fair. Okay, so we're going to test the claim that the coin is fair using a statistical analysis, and you'll see this little piece of language here at a significance of 0.05, and I'll talk about what that means here in just a minute. Okay, so here's how scientists and analysts do this. How do we test a claim about this coin? And we're going to start with a hypothesis. All right, you've probably seen this word quite a bit in a science class where you have a hypothesis that you're going to test. Well, it's the same kind of thing here, but it's kind of weird because we're going to use two different hypotheses, what we call the null and the alternative hypothesis. Okay, so the notation here. All right, we're going to say H with a little zero. They call that a naught. I know, kind of weird, but that's what they call it. So H naught, or what we call the null hypothesis. And then there is H with a little one. Okay. And they call this the alternate hypothesis. So it's kind of like you have a zero and a one. But that is the notation that they use. Some textbooks might put a little A here to indicate alternative hypothesis. All right. So there's this assumption about coins. We assume that coins are fair, and if coins were fair, the proportion of heads that we would see, right, proportion would be 0.5. So you see how the hypothesis strips away all of the context for the problem. There's nothing about a coin in there. There's nothing about heads or tails or anything like that. Our null hypothesis is that the proportion is equal to 0.5. That's all we're going to say there. So then the alternate hypothesis is something different. All right. It would be something that is logically not the same as the proportion being equal to 0.5. So we have a couple of options that we could put here. We could put that the proportion is not equal to 0.5. We could put that it's less than 0.5, or we could put that it's more than 0.5. So based on my experiment up here, I see 80 out of 100. I'm thinking that the proportion is going to be greater than 0.5 here. So I'm going to write that proportion greater than 0.5. So this is our assumption about the population. This is my claim. All right, I'm claiming that the proportion is bigger than 0.5. So that's why we have two hypotheses, one to kind of state what people think or what we are assuming, and something to kind of state that it might be different. All right, and we'll kind of note that here in our notes. This is the claim. Okay. Another thing I'm going to write down over here, and I want you to write this down. This is a right tail test, and don't worry about this yet. We're going to come back to this a little bit later. This is called a right tail test. And the way that I know that it's a right tail test is because I put a greater than symbol here in the alternate hypothesis. And like I said, we'll talk about that in more detail later. Right now, I just want you to put this down here as a note or an indicator. So when you come back and read this later, you have an example of a right tail test. All right. So let's keep going. All right. So before we go any further, we want to make sure that we establish that we can use the normal distribution. We're going to be using the normal distribution to calculate probabilities and things like that later on. So before we do too much work, I just want to make sure that we can actually use the normal distribution here. So the sampling distribution for a proportion normalizes when the number of successes and the number of failures are both greater than 10. So from our experiment, we had 80 successes, right? So number of successes was equal to 80, which means the number of failures was 20, and both of those are greater than 10. So it's normal. And we know the sampling distribution will be normal for this experiment, right? So we're good to go there. Just make sure when you're reading those problems in the quiz or on the test that you are that you have the requirements met for the sampling distribution to normalize. Okay. So now this next thing we're going to do, we're going to find what's called a standardized test statistic. Okay. This is the number of standard deviations that our sample statistic is away from the population parameter. So in other words, how far away is the 80 heads that we got? How far away is that from 50 heads? Okay, so our assumption about the population was 0.5. Our sample statistic was 0.8. So we want to know in terms of standard deviations, how far away is this 0.8 from the 0.5? So to figure that out, we first have to calculate what the standard deviation is for this sampling distribution, right? So what is the standard deviation of the proportions? And this is where we're going to do that p times 1 minus p calculation for the sampling distribution. We divide that by n and square root. Okay, so I'm going to, for this, we're using what we assumed about the population. So I'm going to say 0.5, and then 1 minus p would also be 0.5, and our sample size was 100, and then we square root. All right, so if you do this calculation correctly, you should get a standard deviation of 0.05. So that is one standard deviation. So how many standard deviations apart are these two guys? And that's what we want to know. Okay, so to calculate that, we just take our sample statistic, 0.8, we subtract it from our assumption about the population, which is 0.5, and then we divide by what a standard deviation is. This is very similar to what we did in the beginning of the year where we calculated z-scores. Okay, so if we run this calculation correctly, we should get a 6. Okay, so what this is telling us is that this 0.8 is 6 standard deviations away from 0.5. And if you remember anything from the beginning part of the semester, being 6 standard deviations away from what we expect to see is pretty significant. In fact, it's extremely rare that that would happen. All right. And when we talk about something that's rare and usual, that's when we want to calculate the probability of something, and that's what's coming next. Okay, so we want to calculate the probability of getting 6 standard deviations away from 0.5 if we're assuming that 0.5 is true. Okay, so think about it like this, right? We have this normal distribution from our sampling distribution. Here's our normal curve, right? And the center of this sampling distribution is 0.5. We got a 0.8. Okay? And what we want to know is what is the probability of getting 0.8 or more, right, from this distribution. So we're calculating the area underneath this curve. Well, we know that for any distribution, let's just say we have a generic normal distribution with a center of 0 and a standard deviation of 1, we want to know what's the probability of getting 6 standard deviations to the right. Okay? So calculating these two probabilities are the same thing, and I can do that by taking a normal CDF and setting my left bound to be 6. My right bound will be infinity, right? We'll put in 1E99 for that with a mean of 0 and a standard deviation of 1. Okay. I'll pull up my calculator here, and let's calculate that probability real quick. We'll go second vars. We'll go to normal CDF, and we're putting in our left bound is 6. Our upper bound is going to be 1E99. And then our mean and standard deviation are 0 and 1. And let's calculate that probability. And we get this 9.9 e to the negative 10. It's a very small probability, so I'm just going to put a 0 plus here. So the probability of getting 6 standard deviations away is practically next to nothing. All right. So in other words, the probability of getting a sample of 0.8 when we were expecting a 0.5 is next to nothing. It shouldn't have happened if the coin was fair. Okay? So that's where we make our decision. Since this is so rare, all right, we say since the p-value, right, this is a new term I'm introducing here. The p-value is this probability that we just calculated here. So we call this a p-value, right? But since the p-value is 0 plus, and it is less than 0.05, we reject the assumption that the coin is fair. Okay. So we compare this probability that we calculated here with this significance level that they gave us here. And I said I would talk about this later. This significance level is like a boundary. Okay. At what point do we stop believing what we assumed about the population here? Well, we stop believing it when that p-value gets to be less than 5%. Okay. And scientists will change that significance level depending on their needs. So they might have a significance level of 10% or 5% or even 1% when they want to be really, really sure. But ours was so small, any of those boundaries, we would have ended up rejecting the idea that this coin was fair based on this probability that we got here. Okay, so we would now make an interpretation statement, and we want to make sure that we do this in English, and these are crafted in a certain way, much like the confidence intervals, so we want to be careful with how we word this thing. So we would say there is sufficient evidence to support the claim that the coin is not fair. So that is a hypothesis test from beginning to end. That is the full hypothesis test method there, using what's called a p-value method, where we calculate that probability. Okay, so there's a lot to absorb there. All right, so if you're feeling kind of overwhelmed by that, that's normal. We're going to be talking about different parts of the hypothesis test in more detail in the future videos, but that is one full run through of a hypothesis test. So, like I said, don't be intimidated if that kind of if that was a lot for you. That's normal. We're going to break this down as we go along. Okay. So I like to have this box here where we just kind of break down like each of the major parts of a hypothesis test, kind of like what we did for the confidence interval. So let's run through these real quick. This point estimate that we found, this comes from our sample, right? So when we flip the coin 100 times, we saw 80 heads. That 80 out of 100 becomes our point estimate. So we say p hat equals 0.8, right? And we put the hat on it to indicate that this came from a sample and not the population, all right? Now there's this population claim, or what we are assuming to be true about the population. And if you recall, we assumed that the coin was going to be fair. So we assumed that the actual proportion was equal to 0.5, all right? So just be careful about what you consider to be the claim. This is not our claim. Our claim was that the coin was not fair. The population claim is that it is. Okay, so be careful with what you consider to be the claim and not the claim. All right. The standard deviation of the statistic, we found that to be 0.05. So this is where we did the p times 1 minus p over 100 and then square rooted. So we need to be able to find that piece to do our hypothesis test. And then this next thing, what we call the standardized test statistic, which they will denote with a z for this kind of test because it's essentially a z-score. We found that to be 6 for this problem, and it indicates the number of standard deviations away from this population claim that you are. Okay, so this 0.8 was 6 standard deviations away from the 0.5. And that is a highly unlikely thing to happen. That's where the p-value comes in. We want to calculate the probability of getting this 6. Like, what's the probability of getting something that is 6 standard deviations away or more? So this is where we did the normal CDF. We calculated the p-value to be 0 plus. And make sure when you write this out, just write p-value, okay? Because you already have a p-hat, you have a p for the proportion of the population, and now that you have this p-value for the probability as well. And I don't want you to get those three things confused. That's why I'm using 3 separate notations for them to keep them separated. So hopefully you don't get those confused. All right, the level of significance, they'll usually give that to you in the problem. And like I said, this is your boundary. This is your number that says when you're going to reject or fail to reject that null hypothesis, okay? So if that p-value is less than the level of significance, that's when we reject the population claim, right? We reject this thing right here, all right? So, and they'll set that to different levels, but it's the comparison of these two that makes your decision for you, okay? So those are all the major parts. That's everything that we need to do a hypothesis test. All right, let's do one more. I'm going to do one more run through with this one. So this one is about toothpaste companies. So you've probably seen this before when you bought toothpaste. They usually put it on the box, or they'll put it in the commercial. They talk about all the dentists that recommend their toothpaste. All right. So there's a certain toothpaste brand out there that claims 9 out of 10 dentists recommend our toothpaste. Okay. Now there's a lot of angry customers out there that think that they lied about this, and they're bringing this claim to court. And they went out themselves and talked with 340 dentists and found that 298 of them recommended the toothpaste. So the question is there enough evidence to support the toothpaste brand at a significance of 0.05? Okay. So, all right. So first thing we're going to do is we're going to establish whether or not the normal distribution can be applied to this one. And I think we can, because the people who are bringing this claim to court sampled 340 dentists, and they had 298 successes. Right. So if we're counting up the number of successes here. We had 298 of those, which means that the number of failures is going to be 340 minus 298. So there was 40. So both of those are greater than 10, right? So we would say these are both greater than 10, so normal. And then I'm going to set up my null and my alternate hypothesis. Okay, so I'm going to say H0, H1, right? Or H naught and H1. Okay. And so our population claim, right? This is what we're assuming to be true. The toothpaste company is assuming that 9 out of 10 dentists recommend their toothpaste. So that's what I'm going to put here. I'm going to say the proportion of dentists that recommend the toothpaste is 0.9. This is our population claim. Now, the claim by the angry customers is different. They don't think that the proportion is 0.9. They're probably angry because they believe that that proportion is less than 0.9. So I'm going to say that my alternative hypothesis is that the proportion is less than 0.9. So you'll notice in the first example, we had a greater than, and that was a right tail test. This one is a less than, so this is a left tail test. Okay, so again, keep that in mind. We're going to talk about that in more detail in a future video. All right, so here we go. So this is our null and our alternate hypothesis. Now what we want to do is we want to go and we want to find out what is the standard deviation for our sampling distribution here. So again, this is where we do the p times 1 minus p, and we use the assumption about the population for that. So we're going to say the standard deviation for the proportion is, and we do 0.9, there's our p, times 0.1, that's my 1 minus p, over my sample size, which was 340. And then we square root. There's our square roots. And then we run this calculation. I got a 0.0163 for a standard deviation. That's one standard deviation. So now what I want to know is how many standard deviations away from this 0.9 are we? Okay. So I need to calculate my sample statistic, right? I need to figure out what p hat is, and that is 298 divided by 340, and what I got there was 0.876. So let's pause right there and think about this real quick. Remember, the claim by the toothpaste company was 0.9. Our sample got 0.876. I am kind of thinking that 0.876 is really not that far away from 0.9. I totally believe this could happen in a random sample. I'm not sure that this convinces me that the toothpaste company was lying by any means, right? Because remember, the toothpaste company had assumed that it was 0.9. But I need to figure out how many standard deviations away I am from the 0.9, and that'll give me a more clear picture of how probable this is, okay? So I'm going to take that 0.876. I'm going to take that 0.876. I'm going to subtract it from 0.9 to get a distance away from what we expect. And then I'm going to divide by the standard deviation. So 0.0163. And this will tell me how many standard deviations away I am. And I got a negative 1.5 when I did that calculation. So I'm thinking back to the beginning of the semester, and I'm thinking we typically considered things to be unusual once we were more than 2 standard deviations away. This is 1.5, so I want to take a look at the probability of being that many standard deviations away. I'm not sure if that's really unusual or not. 1.5 standard deviations is kind of far away, but I don't know if it's far away enough for me to reject the toothpaste company, right? Does it breach that 0.05 that we're looking for? All right. And that's where we go next in our test is we calculate the probability of this thing happening. Okay, so we're looking at a normal distribution to calculate that probability. So here's my normal distribution, and I'm just going to use a standard normal distribution here with a center of 0, and we're at negative 1.5 standard deviations away. So here's my negative 1.5, and we want the probability of being that far away or more, right? So I'm going here and finding the area of this tail. right? And you'll notice that this tail is on the left-hand side, which might be why we call it a left tail test, okay? So this is going to be a normal CDF. Our left bound, right, it goes off to the left to negative infinity, so we're going to say negative 1e99. Our right bound is negative 1.501. Let's run that in our calculator real quick. Okay, so I'm going to go to second vars. Normal CDF is option 2. I'm going to put the negative 1e99 in there. And my upper bound is negative 1.5. And then we will paste that in and see how we do. So we got 0.0668. There we go. All right. So with that is the probability of getting 1.5 standard deviations to the left, or in other words, the probability of getting this when we assume this is true, right? The probability of getting 0.876 if we were assuming that 0.9 was true. And we want to take that, that's our p-value, right? So our p-value is equal to 0.0668, and we want to compare our p-value to the level of significance being 5%. Okay, so 0.0668 is greater than 0.05. So this tells us that we did not have enough information to reject what the toothpaste company was saying. It's just not improbable enough. 6%, there's only a 6% chance of this happening, but that's just not rare enough to reject the toothpaste company. All right, so we're going to go ahead and make our formal conclusion. We're going to say there is not sufficient evidence to reject the claim that 9 out of 10 dentists recommend toothpaste. Okay, so there you have it. That's another full run through of a hypothesis test there with all the different steps. Okay, so like I said, there's a lot there to absorb. Might need to watch it a couple of times and run through it a couple of times and see what you're thinking. Think about what questions you have. All right. So I'm going to end the video here, but I'm going to go through just the vocabulary stuff one more time. Our point estimate or sample statistic came from those angry customers that went out and asked their 340 dentists. We found that that p-hat or that sample statistic to be 0.876. The population assumption or the population claim by the toothpaste company was different. They said it was 0.9. The standard deviation of the statistic, that's where we do the p times 1 minus p thing. So we got 0.0163 for that. And then we found out how many standard deviations away the point estimate was from the population claim. So how far away was 0.876 from 0.9? It was 1.5 standard deviations away to the left. That's why we have the negative there. Okay. So then we want to know, well, what's the probability of that happening? And what's the probability of getting that far away from what we expected to see? And that's what our p-value is. We calculated that to be 0.067. And then we compare that to the level of significance, which for this problem was 0.05. So 0.06 was greater than 0.05, which means we did not have enough evidence to reject the toothpaste company's claim. Okay. So that's your quick run through. Like I said, don't get intimidated by this. There's a lot going on in the intro, so we're gonna do some more examples of this and talk about it in a little bit more detail in the future videos. All right, guys, have a great day.